So now we're going to talk about cleaning healthcare data with R. And you might be thinking, didn't we just clean the data? Well, I would describe that more as data munging and pre-processing. When I mean cleaning, I'm thinking a bit about ethical issues like anonymization, which I think you really need to make a clean data set. And I am also thinking about getting rid of mistakes. So the first thing we're going to talk about is record matching. Often health data for an individual, not just often, I would say almost always, will come from disparate sources. So this is true certainly with healthcare data where people receive healthcare, say in many hospitals and many medical practices, but also even if you're a healthcare app, you might be getting data from disparate sources. For example, in the iOS platform, you can get data directly from what people tell you, but you can also get data from HealthKit, which is a central repository that many apps write to. So you find that you are taking data out of HealthKit to use, and that itself is being generated from many sources. So you want to get good at matching people who are the same people, but coming from different data sources. This is a big challenge in research and epidemiological studies and for large healthcare institutions. It's also going to become a problem and is already becoming a problem for larger health apps that have many users, as users do things like forget their username and make a new one, or just create new user identities for their own purposes. Sometimes people like to have a different account on different phones. Not even as a privacy matter, but just because it makes their lives easier for some reasons. But for us as researchers, it's much more interesting and useful if we can match those up and realize they're the same person. So our goals are matching individuals from disparate data sources, but also removing duplicates, right? These are sort of two sides of the same problem. I don't want to count someone twice, which is the same as saying I want to match that person up and realize they're the same person. Workflows on this can be either deterministic or probabilistic, so we're going to talk about both. For deterministic record matching, usually you're going to use this as a dataset dependent methodology. So this can work well when you have specific reasons your data and your identity of people doesn't match perfectly or automatically. In this case, because it's record dependent and because you are actually programming in the rules yourself, you need to account for every variation you'd want to handle. This is a fairly brittle method. If you don't think of something and hard code it, it's not going to get fixed or discovered. So you need to know your data set really well. You need to have strong domain knowledge about how your data sets were collected. This is easy to program, so that's the upside. The challenge again is just making sure you have programmed enough. So we're going to have a coding exercise here, and I would ask you to take at least 5 minutes to think about this and try to code something up. I'm going to do it in R, you're welcome to do it in Python, but I would ask you to do two things if you are comfortable coding. First, think about how you would match this first rule. The first rule is, if the first name or the last name matches across records along with the birthday, define this to be the same individual. So that's one, reasonable way you can say, okay, well, maybe things got misspelled or mistranslated or whatever, but I have few enough people that if I have this kind of match, I feel comfortable saying they're the same. So that's the first exercise. And the second one is, if the initials match and the birthdays are within 1 week, we're going to say this is the same individual. And this is, again, a rule you'd either only want to use because you had some known problems, say with the names but not the initials, or you had some known problems with the birthdays that you knew they would be a little bit off. So think about how you would accomplish those, and then please come back in 5 minutes. Okay, so the data for this exercise is in the GitHub repo that is linked in this section. I actually will be working off a local version, so I will just set my working directory. There are 2 libraries that I used for this. There are other ways to do it. One is the record linkage library, which is written for the purpose of matching records. And the other one is data table, which is a very fast and efficient way of dealing with data frames in R. So you are welcome to use base R, but it's really a good idea to get up to speed with data table. There's 3 sources of data here. We're hypothesizing that we have, say, some canonical data. I'm just going to call that data. We have some data we collected online, and then we have some data we collected in a neighborhood survey. We are going to read those in. And then even before I think about matching, I want to do all of that pre-processing I talked about in the last segment. So we want to convert to caps. We want to remove punctuation, remove white space. So I'm just going to do all of that, please do look at the code at your leisure. And then I also want to sort of make my search space smaller. So for some of the searches I do, I don't want to search the entire data set as I'm matching records, because some records just can't possibly be the same data set, or if I know enough about my data set, I can say they're not. For example, if someone has the initials WW, I am going to say, I believe in my data set, they could not possibly match someone with other initials. So I only want to search other individuals with the initials WW, and that will make my searches and my processing a lot more computationally efficient. And this is a very traditional technique called blocking. So I'm going to create a blocking column, which is just the initials for my convenience later. And now let's talk about our deterministic record linkage. So I said if either the first name or the last name and the birth date match, I want to match those individuals. I'm going to break this up further when I do my code. So first, I want to identify cases where the first name and the birth date matches. So if I take a look at my data, well, we should only look at a portion of it, and then my online data, I can see that the records, the column names are the same, first name, surname, birth date. My online data doesn't have zip code, right, because it was collected online, and I have that initials block that I've added. And for my data, I have the same sources of data plus others. I'm only going to merge on the first name and the birth date. So right now I'm going to say if the first name matches and the birth date matches, I am good to go. So I'm going to use a combined data frame resulting from a merge and call that something sensible like combined data using first name. And now let's look at that result, and I can see I've matched on first name, which only has the one column, and I am also going to make the surname the left surname.x. I'm going to do the same for the last name, so the code is almost identical, except now I'm using surname instead of first name. So now I have two sets of data, combined data using first name and combined data using surname, and now I need to merge those, right? So if you either had your first name or your last name match, I'm going to put you in this group of matched individuals, which is now an R-bind, which is combining the rows from both data frames together. And I'm gonna see how many I've got. I've got 1,749 individuals I matched this way, whereas if I count the number of people in my original canonical data set, that was 20,000. And in my online data set, that was 5,000. So I haven't been able to match everybody this way, but I have matched quite a few people, 1,750, who I might not otherwise have matched at all. One thing, though, I hope you've thought about is, well, what about people who match both, right? Because maybe there were no misspellings in somebody's name, and so actually I would have matched them either by first name and birth date or by last name and birth date. And I can check that by looking at only the unique columns of my data and seeing what the dimension is there. And I can see actually it's a good thing I thought of that possibility, because in fact I have only matched 1,100 people, not 1,700 people. So when you do these heuristic rules where you've programmed something in deterministically, you always have to look for those flaws in your logic as you are combining data. So that's a really easy way to try to match people. You would want to go back and eyeball it and make sure that those matches were indeed correct. You want to decide sort of what an acceptable false negative or false positive rate is and work off of that as well. We also talked about doing matching initials plus a birth date being within 1 week. So here's another case where we can see it pays to be comfortable manipulating dates, and that's why I wanted you to do this exercise. So we've already generated the initials. We just need to compare birth dates. So what we're going to do, firstly, just for purposes of demo, this can be computationally taxing, so I'm only going to take a subset of the online data to match it. I'm then going to merge the online data by the data. I'm going to emerge by initials, and what I'm going to say is I'm allowing Cartesian, because I want every set of matching initials to be joined together. So if there are 40 people with the initials WW in online data, I want all 40 of those to be matched to every W in the original data set. So that's why it can blow up very quickly. But this will allow me to use that birthday requirement as the comparison. So I will generate all combos. And then what I'm going to do is I'm going to generate a birth date from both the left-hand side, the data, and the right-hand side, the online data. Make those birth dates as date. So if you can see what I've highlighted here, as.date, it's a date format. So now I'm working with it as a date rather than as a string. I'm going to combine those. One thing I'll note, if you eyeball this, you're going to note that some of the birthdays are in the future. That is a quirk of R. If I were to say 8/24/50, it's going to read that as August 24th, 2050 rather than 1950. Because I am only doing time differences, time deltas, for me that doesn't matter, but if you actually cared about the birth date, you would have, of course, want to fix that. So I'm going to just calculate what I'm calling the birthday delta here. It's going to be the difference between the left-hand birth date and the right-hand birth date. And I'm going to convert that to as numeric, which is going to give me the dates, the days. So let's do this. And if we look at all combos, we can actually see the birthday delta. And we can see in most cases they're actually pretty big, right? For example, a birth date in 1976 versus a birth date in 1989 is giving me an absolute difference of around 4,600 days, which makes sense when you realize there's about 360 days in a year. So that checks out. And now what I'm going to do, and this is why I really like data table, is it's easy to do logical operations, as you can see here. I am going to only select those rows where the birthday delta is less than 7 and greater than -7, right? And I could have just taken an absolute value, but this is how I'm doing it. So I'm going to subset down just to those. And now I can take a look at all combos. And I can see I'm mostly looking at people who have a birthday on the same day or within very short days. So for example, if we look at the first row, we're comparing Amy Anderson with a birthday of Jan 11th, 1989 to Amy Anerston with a birth date of 1989. So in this case, I say, yeah, that's probably a match, right? One of these last names is probably just misspelled, and the birth date has helped me to get there. So if I then think about how many people I have matched, it's 971, which is a low number, but seems reasonable given what my requirements were. So I probably haven't matched everyone, but I have gotten part way there. I can also easily sort by the first name and last name like this, and say I want to look for common names to see how they did, and confirm I don't have extras. I, for example, know Brown is a very common name, so I say let me look at all the Browns and look for the possibility that I have matched the same person more than once, because that's something I haven't ruled out with my heuristic. But looking at this, I think it's looking pretty good. So I've got Amanda Brown, Amy Brown, et cetera, et cetera. I do have certain names in common, but if I look, I've got 2 Christopher Browns, but their birthday, ignore the 2040, right? That's really 1940 and 1947. I can actually, I can see that they were born many years apart. So it's very unlikely that somebody not only had maybe a name misspelled or not, but also had their birthday changed by 7 years. That's fairly unusual in most records, although not entirely unprecedented. So I'm feeling pretty good about this sort. Similarly here, I've got 2 James Browns, but it's 73 versus 65. So as a first pass, this would be fairly good performance for a deterministic way of sorting your records. So we've just seen deterministic record matching. It can be a somewhat laborious process because I have to know my data set really well. I have to think about sort of what are reasonable ways to match my data, and I also have to do a lot of checking after the fact to make sure that my rules didn't incorrectly match people, and even more laboriously see how many people should have been matched but weren't, which is an almost impossible task, checking by hand given the dimensions of the data. What works much, much better in most cases, especially in cases where I don't know why the data would be mismatched, is to do probabilistic record matching. So what I do here is generate a likelihood measure that 2 records match the same person. There's many ways to do this. There's many statistical papers about it. The point for today is to understand that it will give a likelihood, so I don't need to know the full metrics of my data. I don't need to intimately know my data to come up with good record matches. It also handles missing data, which can be very advantageous. Some advantages over the deterministic record matching we've just looked at: it handles unknown qualities of the data set, so things that you just can't notice. We humans are really limited, especially when looking at massive components of data. We don't always see trends. We don't always see why things went wrong. It can also evaluate the relative strengths of different matches. So for example, in my hard-coded record matching, there was a possibility I would have duplicates, and I had to look for them or sort of decide I was okay living with that. With probabilistic record matching, your algorithm will take care of finding the most probable record per person and won't match one person to many others. It will enforce that logic. How do we do this? You need to pre-process to choose linking keys. So we did that. We said that we were going to pre-process by making an initials column. That's a way to limit the search space, right? You are only going to search, say, within initials is one logical way to do it. And that can take something that would be sort of impossibly computationally taxing and dial it down to where it's possible and reasonably fast. You also need to think about how you want to do your comparisons. Often you're going to use string similarity on names. You can also use date comparisons like we did with birthdays. You can also use date comparisons on date of treatment or date of military service if you're looking at military records, or date of use if you're looking at an app case. And finally, numeric comparisons. So if you have Amy Brown, who weighs 126 pounds, and then you have Amy Brown Da, who weighs 128 pounds, that's probably the same person, and it makes it more likely that, say, the weight matches in addition to the name being similar. So the more metrics you can use for comparison, the better your record linkage can be. And what you do then is you make a final prediction by setting a cutoff score. So that's the final thing you need to provide, and you provide that halfway through the process, and that's where your judgment comes in. Some knowledge about how important accuracy is, whether false negatives or false positives are more worrying, and how you want to set that cutoff score to get the right balance. So we're going to take a look at a code example here, and again, that is in recordlinkage.r, the same file we're already working in. So as a reminder, we imported the record linkage library, but we hadn't actually used it yet. The record linkage library is for probabilistic record linkage, and I'm going to show you just how easy and straightforward it can be for a simple use case. So in this example, I want to now compare my data to my neighborhood data. And let's say, thinking about the structures here, I want to show you. So we have data, and remember we have birth date and zip code in addition to name. And then if we look at neighborhood data, we have first name, last name, and zip code again. And I'm going to hypothesize that for neighborhood data that was collected by people going out with their clipboards and surveying, that they were pretty sure of what zip code they were in. So I'm going to postulate that zip code is a fairly reliable thing, just like initials. And so what I'm going to do when I do my comparison linkage is I'm going to compare my data, and I am going to set as my blocking fields zip codes and initials. And what that does is it says you don't even have to search all matching initials. You just search all matching initial zip code estimates. So for example, I'll only search KDs who are also all in 11226 or all in 11227. And so that is enormously scaling down on the computational power you need. So let's go ahead and run this comparison linkage where we are creating comparison vectors. And you'll see there was still a bit of a lag, but this is much better than if I hadn't been able to include my neighborhood data. What you see here is you see initials and zip codes have to match. Those are my blocking fields. You see the row IDs from the two data frames, and then you see an indication of whether they match. We then want to calculate the agreement weights based on the comparison vectors. This gives us an idea of what sort of weights we want to use. And one thing you want to notice is hopefully you're in a situation where things are like a very good match or not a match at all. So what we're going to hope for when we look at this is weights that have sort of a bimodal distribution. So we're going to first run this expectation maximization weight calculation. This is a little too complicated to explain in the space of a short code demonstration, but it basically tries to figure out the likelihood that things match given how common the attributes you're using are. So for example, matching on the last name Brown is not as good as matching on the last name, I can't even think of it, but a very rare last name. Or matching on the name Aileen is much better than matching on the name Joe. So this expectation maximization takes into account, the fact that Johns are much more common than Aileens. So we are going to calculate those weights. And you can see it's still computationally demanding to go back and forth and figure out which individuals should be matched with which other individuals. That has finally completed, and we can look at the summary. This is the distribution. If you look here, what I really like that we had talked about is the fact that I would really hope this is bimodal, which it is, right? So the weight distribution is running from -1 all the way up to 12, but what I notice is there's one cluster here, say in the -1 to 2 range, and then there's another cluster here in the 7 to 10 range, and that makes me feel really good because I think one of those clusters is the matches and one of those clusters is the non-matches. And there's sort of 52 people in this dodgy area 3 and 4, so I'd probably want to look into that if I had more time, but this is largely bimodal, which I'm really happy about. Our final step is we do get pairs, and we're going to stick that in a variable called neighborhood pairs. This also takes a second, calculating those pairs. And now let's look at those pairs. So now what this has done is that it has come up with these weight distributions. It has matched each person to only one other person, maximizing our expectation of likelihood. And it's giving us some weights. And so looking at these top ones, these look pretty darn good. John Edwards versus John Edwards. But I can see they're both in the same zip code, or the top matches, they actually just match completely. So what I'm going to want to do now is I'm going to think about what's a good weight cutoff. So I just eyeball things. I'm looking at the top 10. That's probably not where I want to start. I probably want to start maybe in 1,000. Looking at these weights, now I'm seeing Kenneth Smith and Jecriel Smith. That's probably not the same person. Or Janice Edwards versus John Edwards. That's also probably not the same person. So when I'm thinking about where I might want to do my cutoff, I'm thinking, well, those don't look so good, so I might cut it off there. Maybe I'll go back up to 500. These are looking more reasonable. Marie Harrison versus Mary Harrison, I'm very willing to believe that could have happened. Mark Moreno versus Mark Moreno, that looks reasonable. So what I would normally do is poke around until I find what seems like a good minimum weight and a good max weight. And I'm going to, for purposes of the demo, cut it off here. So I'm going to say my weight of 9.5 is where I want to put my min, and my max I want to put up at 12 to get all of the highest. So now I can do this get pairs, where I'm actually telling it the max weight and the min weight. So now it's going to cut it down for me using those max weight and min weight. So I can look at my final pairs. I see at the top these really excellent matches. And I'm going to look at the tail, which is going to be the worst, and see how they are. Virginia Robles, Thomas Gardner, these also seem very good. Usually you want to not be entirely happy with your tail, so probably if I had more time, I'd sort of explore a bit more and find, depending on my application, what the cutoff is. Now, one thing you want to think about is how important your false positives and your false negatives are depend on what you're trying to figure out. So for example, if I'm trying to match up someone's entire life of medical records, and that's the purpose of my study, it's probably more important to be over-inclusive rather than under-inclusive. On the other hand, if I am trying to do an experiment to measure the efficiency of a drug before and after treatment, and those are in different tables, I probably only want to include people where I'm really sure, because the cost of a mismatch there would undermine my fundamental conclusions. So depending on what your use case is, you will have different tolerances for mistakes. So we can see that actually probabilistic error matching is easier to do code-wise. It is certainly more complicated statistically, and you want to feel comfortable with how that works before you deploy it in production, but it's usually the way to go because it is less error-prone. Now that said, there are a few caveats. you need to understand how to propagate error into your downstream results. And this is also not the easiest thing to do. So for example, in the medical treatment case I just talked about, you'd want to be really careful when you're thinking about the effect of a medication to think, well, how could mismatches of people have affected that? You also want to remember that not all individuals are equally likely to be mismatched in the first place, right? Probably certain healthcare centers have higher rates of typos, or maybe certain ethnicities have their names more likely to be misspelled. These are the sorts of things you want to think about because you want to make sure your analysis does not propagate these sort of built-in biases. You also should keep in mind that with a labeled training set, you can explore other newer machine learning options. So this probabilistic record matching is an expectation maximization technique, but you can also look into things like neural networks. These have shown really great performance, but they do need that marked training set. So if you have a use case that's really important and you can deploy resources to have humans match training data, that's also something to think about. We will quickly look at anonymizing data. This is something you also want to be aware of for a data pipeline. It's important to protect identity while also, when you can, preserve associations in the data, right? If there is structure, you want to keep it there. So you can't just randomize. You should remember that in the US, for example, if you have DOB, gender, and zip code, that can identify 90% of people. So you might think you've anonymized your data, but actually often people who are interested in these sorts of issues can very quickly figure out who someone is even after you've de-anonymized data. And this has often been a problem even in research and academic data sets where people realize after the fact that they can match up personal information like credit histories or medical records to actual people, and it's not that difficult. The standard is k-anonymity. For k-anonymity, the definition is that every row has to be indistinguishable from k-1 other rows. So at most, an individual could be discovered to be one of k rows. So you might be able to say, well, I'm looking at women at a certain age range who live in a certain neighborhood, and they can identify me as being maybe one of 20 of those women. But that wouldn't be enough for them to know, say, my HIV status or my diabetes status. So you could argue that that still preserves my anonymity. And how you set the value of k probably depends on the sensitivity of your data. So the good thing about k-anonymity is it guarantees your data is accurate. How do you do this? How do you create k-anonymity? There are three main techniques. One is suppression. You just don't give out certain data. For example, if the DOB is really revealing, you just don't reveal dates of birth. You tell people, oh, well, this person was born in this year, and you leave it at that. You can also do generalization, converting values into bins. So for example, rather than indicating someone's exact date of birth, you might say January 1994, rather than January 17th, 1994. You can do a variety of perturbations. One is microaggregation, where you collect people together who are similar, and then you scramble their values. You can also just do direct data swapping between individuals. So two individuals within your k-anonymous group, you just swap their data. For example, you swap their blood sugars or you swap their heights or whatever. You have to be careful about what you swap though, because you don't want to remove association. So the things I said are actually wrong. If I were to swap the height or the weight or the blood sugar, now I might come up with correlations that aren't really true. I want to swap things that could be used to identify people, such as perhaps a date of birth or a zip code, things that are not relevant to the structure I'm trying to study. So this also is something where you need to balance anonymization needs, but also the needs of researchers. And finally, you can add noise. Adding noise alone is never enough to generate k-anonymity. It can be tempting to take the easy way out, but it doesn't work so well. So that's more of a supplementary technique. And I will just add that Python and R both have packages for generalization and perturbation. So this is a very easy thing to do in practice.